Hello everyone and welcome back to Dynamics course MIE100. My name is Noor. For those of you who don't know me, I'm going to be the video TA for this course. I was also the video TA last year. You can check out my previous videos from last year. Basically, what I'm going to be doing is I'm going to be solving your tutorial problems again with you in the video. For those of you who might have missed their tutorial or who just want to look back for an explanation once they're studying or they're reviewing for their midterms or exams. A little bit about me. I did my undergrad in biomedical engineering at the University of Ottawa, and now I'm doing my PhD in mechanical engineering at the University of Toronto. I'm also specializing in soft robotics for medical applications, and I think dynamics is going to be a very interesting course for those of you who understand it. I hope that these videos help you. I'm going to be trying to explain the concept as much as possible, but of course, if you have any questions, you can always either email me or leave a comment in the comment section below. And yeah, that's my introduction and we'll get started. For the very first tutorial, the problems are going to be focused on kinematics of particles, specifically the rectilinear motion equations. I'm going to be solving the tutorial problems with you in details. And as always, if you have any questions, you can always drop them in the comment section below. All right, so starting with our first problem, we've got a steel ball A of diameter D sliding freely on the horizontal rod leading to the pole face of the electromagnet. The force of attraction obeys an inverse square law, which means the acceleration of the ball is going to be this function over here, where k is the measure of the strength of the magnetic field. If the ball is released from rest at x equals to 0, determine the velocity v with which it strikes the pole face. All right, so right here we know that this equation over here of acceleration is equal to k over L minus x all squared, where k is the strength of the magnetic field, and a is the acceleration. Now this acceleration is only when the ball A is released from rest at x equals to 0. Basically, we want to find out what the velocity is at B. All right, so to be able to find that, we're going to have to be using our rectilinear motion equations. Now, what are our rectilinear motion equations? These are equations that can be applied when the acceleration is constant. Our first equation is v is equal to dx over dt, where v is the velocity, t is time, and x is the distance. So it's basically the derivative of x, or x dot. That's our first equation. Our second equation is a acceleration is equal to dv over dt, which is the derivative of v dot. And this is our second equation. And basically, when we use these two equations and basically sub in 2 and 1, we're going to get a new equation, which is v dv is equal to a dx. This equation over here is very important to remember. And this is the equation we're going to be using to find the answer for our problem. Now, when we have VdV is equal to AdX, the obvious way to solve it is by integrating. So we find the integral of V with respect to dV, and A, which is, we know from here, is k over L minus x, all squared. With respect to x. And our boundary conditions are 0 to xb and 0 to vb. The integral of v is going to be v squared over 2. And for the integral of a, we're going to use the substitution method of integration, which means we're going to substitute this L minus x with u. So u is going to be L minus x, and our du over dx is going to be equal to minus 1, which means that we're trying to find the integral of minus k over u squared with respect to u, which gives us k over u. Now we sub it back into our equation to give us k over L minus x. The boundary conditions are 0 to xb. Now when we insert our boundary conditions, we're going to get vb squared over 2 is equal to k over L minus xb minus k over L. Let me turn the writing to black so that it's easier to read. Now we're gonna try to simplify this equation. So vb squared over 2 is gonna be equal to k xb over L multiplied by L minus xb. Now we want to find xb in terms of L and d, or in terms of whatever we have in our first problem. If we look back to our little diagram, we have the distance L, but we want to actually find the distance xb, which is this distance over here, from our initial position to our final position. Now if you look very closely, this really means that xb is equal to L minus this distance over here. This distance over here is just going to be half the diameter. So it's L minus d over 2. Now we'll be able to plug that into our little equation. To get vb squared over 2 is equal to k L minus d over 2 and now we're going to clean that up a little bit to get 2k multiplied by L minus d over 2 all over L d over 2, and our final answer is going to be vb is equal to 2 multiplied by the square root of k L minus d over 2 over L d. And now for our second problem, we've got a freighter that is moving at 4 meters per second. After the engines are shut off, it decelerates proportionally with the square of the velocity, which means the acceleration is equal to minus kv squared. If it takes 10 minutes to reduce its speed to 2 meters per second, find the distance traveled in those 10 minutes and its speed as a function of time during the travel. Now to summarize, we have v1, our first velocity, is equal to 4 meters per second. We've got our acceleration is equal to minus kv squared. And at t2, which is 10 minutes, v2 is 2 meters per second. And we want to find the second distance, x2. And we want to find the velocity, the function of velocity as a function of time. All right, so as usual, we're going to be using our rectilinear motion equations. And we're going to start with A is equal to dv over dt. And from that, we know what A is. So we're going to substitute our A with minus kv squared equal to dv over dt. And then we're going to find the integral of minus k with respect to t equal to the integral of 1 over v squared with respect to v. And our boundary conditions here for our time is 0 and 10 minutes, which is 60 multiplies by 10 to give us our time in seconds. So our velocity is going to be from 4 to 2, because our first velocity is 4 meters per second, our second one is 2, so it's decelerating. And that's going to give us minus kt from 0 to 600, and minus 1 over v from 4 to 2. Once we plug in our boundary conditions, we get minus 600k is equal to minus a quarter. And we get our k, which is 1 over 2,400. Now to find velocity as a function of time with no boundary conditions, we're going to do the integral again, but without boundary conditions this time, to find the general solution. And that gives us minus kt plus c is equal to minus 1 over b. Now, if we rearrange this equation, we get the velocity is equal to 1 over kt plus c. Now, to find c, all we need to do is plug in back our k, which we found, and one of our boundary conditions, the easiest one being 2 and 600. 2 is equal to 1 over k, which is 1 over 2,400, multiplied by our t, which is 600 seconds, plus c. And that's going to give us the value of c, which is a quarter. And now for our answer for the velocity as a function of time, we have vt is equal to 1 over 2,400 t plus 1 over 4. But that's not the end of our problem. We still want to find x2, or our final distance. So we're going to be using the rectilinear motion equations again. Which is v is equal to dx over dt, or the derivative of x. We're going to plug in our value for v that we just found. we're going to integrate. With no boundary conditions. We're going to use the substitution method for this integral to make our life easier, and we're going to be substituting this expression over here. So our u is going to be equal to 1 over 2,400t plus 1/4, which means that our du over dt is going to be equal to 1 over 2,400 Now we're gonna try to integrate 2,400 over u with respect to u, which is gonna give us 2,400 ln u. And then we're gonna plug in that again into our main equation and substitute u with our expression. So that's gonna be 2,400 ln t over 2,400 plus 1 over 4 plus c is equal to x. Now, to find our c, we know that at x naught, so before this whole freighter started moving, our time must have been 0. So we're going to use this boundary condition to then plug in into our equation to find our c. And now that we found our c to be 3,327, we're going to plug it in back to our equation to find our x2, which is going to give us an answer of x2 is equal to 1,663 meters. In our third problem, a marksman fires a practice round from A towards target B. If the target diameter is 160 millimeters and the target center is at the same altitude as the end of the rifle barrel, determine the range of shallow launch angles for which the round will strike the target. Neglect aerodynamic drag and assume that the round is directed along the vertical center line of the target. Note the word shallow indicates a low-flying trajectory for the round. Now, this problem might sound complicated at first, but let's just try to dissect it. Now, we know that this is going to be our target. Let me draw a proper circle. And this is the diameter of the target. Now, we want the person to shoot at the center. However, there's a range of angles of theta where he can shoot anywhere along on the target from here to here. To find that, we're going to have to be using our rectilinear motion equations for constant acceleration again. But let's rewrite what we already know. We know that our initial velocity is 900 meters per second. We know that our length L from the person shooting at A to the target at B is 1,500 meters. And we know that the diameter of the barrel is 160 millimeters. And we also know that theta must be small. So what is the range of theta that the shooter could shoot at to hit anywhere on the target? We're going to use our rectilinear motion equations. And we know that dx is equal to b dt. Right? This is just rearranging v is equal to dx over dt. So from this equation over here, we can integrate dx to get x is equal to x naught plus v naught t. This is a very important equation that we're going to be using. Now, another important equation is going to be the same thing, but instead of using dx, we're going to be using dy because he's shooting at the y from the y-axis, right? So you've got dy from y naught to y is equal to v dt, but now we've also got acceleration because this is not at a constant velocity anymore. When he's shooting something vertically, we've got gravity to also consider. So that's going to be our acceleration term over here. Technically, we have an acceleration term over here as well, but because this is in the x-axis, there's no acceleration at play. So to simplify or integrate or find the integral, we're going to get y is equal to y naught plus v naught times t plus the acceleration, which is half gt squared. This is another very important equation that we're going to need to remember for future problems. Now that we've established our equations, we need to find t and theta at the bottom of the target first. So here's our target, that's the center, and we want to find what t is going to be equal to and what theta is going to be equal to if you shot at the very bottom of the target. We're going to use the x equation over here, and we know that x, the distance between A and B, is 1,500, and we know that the initial distance is 0, and we know that v naught, our initial velocity, is 900 cosine theta multiplied by t. Now why is it times cosine theta? Because he's shooting the velocity at an angle. So the velocity in the x direction is going to be equal to 900 cosine theta. And in the y direction, it's going to be 900 sine theta. And that's going to be our first equation. And now we're going to be using our y formula. So our y is going to be half the diameter of the target, which is minus 0.16 over 2 equals to v naught, which is 900 sine theta, because we want vy, multiplied by t minus half the gravity, 9.81, multiplied by t squared. That's our second equation. Now we're going to use our simultaneous equation to sub 1 into 2, and we get t is equal to 1.667 seconds, and theta is equal to 0.517 degrees. Now we want to find t and theta at the top of the target. So over here, assuming he shot at the very top. We're going to use our same method again. So using the x equation, we're going to do 1,500 is equal to 900 cosine theta 2. And this time, our y is going to be 0.16 over 2, positive, not negative, because we want the top, not the bottom, is equal to 900 sine theta multiplied by t minus half 9.81 t squared. That's our third and our fourth equation. And we're going to find the simultaneous, we're going to solve our simultaneous equations to get t is equal to 1.667 seconds, and theta is going to be 0.524 degrees. Oops, sorry. Nope, never mind. That's right. Now that we found our two thetas at the top and at the bottom, our range is going to be 0.517 theta and 0.524 degrees. Our fourth and final question, we've got a projectile is launched from point A with the initial conditions shown in the figure. Determine the slant distance s, which locates the point B of the impact, and calculate the time of flight t. Now we know that our initial velocity is 120 meters per second. We know that the length L from A to the slanted side is 800 meters. We know that theta that the projectile was shot at is 40 degrees. And we want to find the slanted distance s from the start of the slant to B. And we also want to find the time it took for it to go from A all the way to B. So we're going to use the rectilinear motion equations that we talked about in our previous questions. If you remember, we've got xb is equal to xa plus vxa multiplied by t. We've also got yb is equal to ya plus vya t minus half gt squared. And we're going to use those equations and plug in our known values to find s and t. So first of all, we know that for x, it's going to be 800 plus s cosine theta, because we want to find the horizontal distance. So s cosine 20 is going to be equal to 120 cosine 40 t. So we want the vx to be in the x direction. We're going to do the same thing with y. Now, yb is just going to be equal to s sine 20, and it's going to be equal to 120 sine 40 multiplied by t, because we want vy, minus half the gravity, 9.81, multiplied by 2 squared. This is our first equation, this is our second equation. And we solve our simultaneous equations to find our answers, which are S is equal to 455 meters, and T is equal to 13.35 seconds. That's our final answer and the end of our tutorial problems. That was the end of our tutorial problems. I hope you found this video useful. Please, if you have any questions, don't hesitate to email me at noor.dawidar@mail.utoronto.ca. You can always also leave your questions in the comment section. And yeah, see you next week.